First of all, I would like to thank the organizers for organizing this wonderful event. And as Kolia was mentioned, that I'm really I heard about this institute, and this is my first time to be here, and I've seen this wonderful place. And so today I'm going to talk about the joint work with Yinlong Liu and Jian Zhang, and okay. Okay. So, all of us we know that we had one of the main things in representation theory is Schur-Weyl duality, and you can study the representation theory of Lie algebra, feel the representation of the symmetric group in that case, and then if you look at the Schur-Weyl duality, and then the decomposition is to give you some information about the correspondence between the representations. And actually, later, there was also another correspondence formulated by Littlewood, which is very much like a Littlewood, like Schur-Weyl duality. And in some sense, and may provide slightly more information. For example, that if you take the multiplication of two representations, and then from Schur-Weyl duality, then you don't get exact information. And then what Littlewood is doing is he can actually provide information about the multiplying, in other words, about the multiplying two representations. So let's see that. So I will try to do this. So first of all, I'll start with the. I think this. Oh, okay. There's a immanent. Immanent was actually first formulated by Schur in his paper 1918, and he defined at that time he didn't give the name of immanent. The name of immanent was given by Littlewood in 1940s, and it's defined that you take any irreducible representation of symmetric group as n. That's parameterized by a partition of n. And the so-called lambda, say that the partition lambda, the lambda immanent is this formula given by the summation. Is like it's a summation of all these product. And over here, this in the particular case, if you look at the sign representation, then the character will be plus minus. In that case, the immanent will become determinant. If you look at the trivial representation, then the immanent becomes permanent. So then Schur actually proved that in general case, if you consider n by m positive semi-definite Hermitian matrix A, he proved that the normalized immanent is the determinant is bounded by normalized immanent. And that's in this paper of 1918. And later, Lieb also had a similar result about the permanent. So his result says that the permanent of n by m matrix, in that case, it's defined by it's just sometimes permanent is called the pure determinant, the absolute determinant. And then he actually conjectured in 1966, saying that for any positive definite Hermitian matrix A, the normalized immanent is bounded by permanent. So in some sense that you have a determinant is one extreme and the permanent is another extreme. And then in general, the immanent is somewhere in between these two things. And that's, of course, this is his conjecture. Now, let's look at another interpretation of immanent. This formulation is given by Kostant. So let's take a irreducible representation of SLN. So the representation space is V lambda. You have a homomorphism from symmetric group from SLN to the GLMV. And then if you consider the Kostant subgroup, or meaning that the group of diagonal matrices, and over that, and then that space V lambda is decomposed as direction of the weight spaces. In particular, let's denote the weight space. This is there's a special weight space called the zero weight space for the representation. We denote that by V lambda H. There's a V lambda H. There's a V lambda H. Then you can consider the projection from irreducible representation to the zero weight space. And then Kostant proved that for any matrix in the SLN, the immanent of matrix A can be given by the trace of the projection times the irreducible representation, then times projection. And in particular, using these, you can prove that the trace is actually bigger than the dimension of the zero weight space. And here, of course, that whether A is either positive definite or totally positive. And so then there was a question. This is the interpretation for the zero weight space. And then there was a question: what about the non-zero weight space? Whether there's some connection with this. So that was a problem and raised. And so actually, part of our work will be answer that problem and also try to generalize that this quantum case. Yeah. Yeah, that we're going to talk about that later. Yeah, that's what actually we're going to solve that problem later. This is the Kostant's interpretation is about the zero weight space, and we're going to have a result for general weight space. So let's look at the Littlewood correspondences. Littlewood actually formulated 3 correspondences. The Littlewood correspondence 1 saying that given any relation among Schur function, as we know, the Schur function is the character of the irreducible representation. In other words, given any relation among representations, and then you can replace the Schur function by corresponding immanent of the complementary principal minors. And provided you take and every product is sum of all sets of complementary principal minors. And that's the Littlewood correspondence 1. So for example, suppose that we have you modify 2 Schur function, and so like you can see the Littlewood-Richardson rule, and you have this decomposition, and then you immediately you will get the same similar relation by replacing Schur function by immanent. So you got this in this field the Littlewood correspondence. Then you get the following relation for the immanent by the I1 and I2 are taking all summation over all disjoint the subsets of I1 and I2, and the corresponding the cardinality of the will be the partition of mu and partition of nu. And so this is the one of the correspondence for from the Littlewood correspondence, and then his correspondence really tell you that information among the representations. And so suppose you have some relation among representation, and then he says that you can just literally get a similar correspondence from the immanent. Of course, on the other hand, if you know some relation from immanent, you can also get information about the representations. So this is his the correspondence 1. Then he also have the correspondence 2. So let's take AI to be generalized submatrix of A, whose rows and columns are indexed by this. By generalized matrix, I mean that usually when you have a matrix, you consider submatrix. In that case, your submatrix is really a subset of the original matrix. The so-called generalized meaning that I can repeat some of the rows and some of the columns. So by that I mean all the rows and columns can be with some repetition from the original matrix. So then corresponding to any relation between the Schur functions, we may replace each Schur function by the corresponding normalized immanent of the corresponding principal minors, and provided we also take the corresponding sums over all the complementary principal minors. So for example, if we have a multi-set of n, so this is some with the repetition of the indices and the multiplicity of 1 is m1, multiplicity of n is mn. You have this multiset of n. And then we denote the product of multiplicity of the index. By that, I denote as mi. And suppose we have a relation among the multiplication of two Schur functions, then immediately we also have a relation for the immanent product of immanence of the summing over all the I1 and I2 with the then dividing by the multiplicities, and that really getting rid of the multiplicity, and because that's the. And then on the other hand, we have this the immanence for the corresponding to the S lambda, and then with the same coefficient, with the same Littlewood Richardson coefficients. And then finally, there is really an exact correspondence between immanence and the Schur function. So Littlewood correspondence 3 saying that for any partition R, the lambda is a partition R. Suppose that we have this matrix A. Let's suppose that the characteristic roots of A is omega 1, omega n. Then the Schur function in the variables omega 1, omega m can be expressed by immanence. So in this way that you can express Schur function in terms of immanence. And the sum is taking all the multisets by dividing all the multiplicities. So all these correspondences actually formulated in his book, this book in 1940. So now we have the question is that so here we have this correspondence between Schur functions and immanence, and this is really for general linear group and the symmetric group. So then the natural question is, can we generalize the same thing to quantum algebra of general quantum linear algebra and Hecke algebra? So that's our question. There are some early attempts to try to do the same thing. So first of all, let's try to see how we define immanent, so-called Q immanent. So before that, actually, before that question, there is also immanent correspondence actually implies several well-known identities. So one of the identities is called the Littlewood-Merris-Watkins identity. Suppose we have an induced character from the sign character and trivial character from the Young subgroup as mu to the bigger group. So that's denoted by phi mu and phi psi mu and phi mu. Then from Littlewood correspondence 1, we can get this identity. So in other words, this identity really tells you that you can compute. Remember that the phi psi phi mu is sometimes is an induced character from the sign representation. Then you can express that as the immanent of that by in terms of determinant of the smaller. In other words, from the Young subgroup, the part of information from the Young subgroup, you take the determinant over that. And then there is a similar result for these for immanence for permanent. You can express immanence for the induced character for the trivial representation, and then in terms of permanent. So this is the one thing. And then another thing that so there are some attempts to do this. So first of all, there was a result by Kavalinka and Skandera. So they consider for the multiset of n and then fixed partition of I, then the immanence can be expressed by this determinant. So then this is because I couldn't put that, and then this is correspondence for the trivial character. So then we know that actually the immanent for Hecke algebra was defined in the late 80s by Hammond. And he defined the trivial. You can just really replace the character of the symmetric group by the character of the Hecke algebra, then you can immediately define something called the immanent for Hecke algebra. So then one of the work for this Kavalnika and the Skandara say they are trying to generalize these Littlewood identity, Littlewood correspondence for the immanence for Hecke algebra. And so they were able to prove for the in other words for the sign character case and the trivial character case there are some correspondence, but unfortunately their definition of the immanent, the Q immanence or that did not work in general. In other words, they cannot prove the general Littlewood identity. So let me, before we do that, let's also look at another relation with the Littlewood correspondence. This is Macmillan's master theorem. So you can suppose that you have the alpha 0 and beta 0 equals 1. I mean, for k equals 1, and then you get a 0, and then for k greater than 0, it's defined by this alpha k by summing over the determinant of the minors, and then we also sum the determinants over the modified permanent. And Macmillan in 1916 he proved his master theorem by this alternating sum. And then also there is a Goulden-Jackson identities. Suppose that you fix a partition lambda, and you denote that this alpha and beta were defined over here. This alpha and beta are defined here, and then you can form the matrix. This matrix is like a Jacobi-Trudi-like matrix. You have a Jacobi-Trudi-like matrix. Usually, then if you take the determinant, you can get a Schur function or something like that. So here you can take the that Jacobi-Trudi type matrix A and B for the beta B, and then you take the determinant. He proved that the determinant of A and determinant B are equal and can be expressed by immanent. So these are the in fact, all these identities, they are closely related to Littlewood correspondences. So now let's try to solve this problem for quantum case. So we consider I consider the quantum coordinated ring. So this is the quantum matrix, n by n matrix. So I start with R matrix. This R matrix is a matrix in the Cn is a n square by n square matrix. It's written by this Eij is the union matrix, and then so we can express this R in terms of tensor. In this Q and this is the usual R matrix, and this R matrix satisfies the Yang-Box equation. Here the Rij means that because R is the tensor on Cn cross Cn acting on that, so Rij meaning that only R acting on the ith copy and jth copy, and the remaining copy are this Rij acting on the as identity. So then you have this this Yang-Box equation. Through this Yang-Box equation, and then you can consider the so-called the RTT relation. I'm going to use X here. So you consider the so-called quantum coordinated algebra AQMTN is generated by Xij subject to the relation Rx1 times X2 equals X2 and X1. In other words, this relation tells you that the commutation relation between X1 and X2, X1 and X2 are really sort of like they satisfy certain like a locality, and then you have this conjugate. In other words, x1 times x2 is equal to x2 times x1 by conjugation by R matrix. And then if you write down all these xij in terms of the matrix elements, and these are the matrix elements, you have the six all these this relation. So it really says that along each row or along each column, the matrix the entry is Q commute, and on the skew diagonal, the matrix element purely commute. On the main diagonal, the commutator is equal to the Q times the Q inverse times the skew diagonal corresponding element. So this is for all the I less than j, k less than l. And then the so-called quantum coordinate algebra is defined by the algebra generated by xij, and xij, I and j running through 1 and n. They satisfy all these relations along this I less than j and k less than l. So this is really something like a quantum semigroup. You have consider m by m matrix, and then they form a semigroup, and this is really the quantum version of semigroup, and we call that the quantum coordinate algebra. So then for quantum immanent, there was some early attempt, as I mentioned, that Kavalinka and Skandera defined the immanent in that way, in this formula. And then using these, they obtain the Q Littlewood-Merris-Watkins identity and the Q Goulden-Jackson identity, not in the quantum algebra, but in some quotient algebra of the quantum algebra. In other words, this immanent, although you define this immanent in this way, but you don't get the quantum Littlewood correspondence. You only get the quantum Littlewood correspondence. You have the modulo sum relations, not directly on the quantum group, but on some quotient of quantum group. So then, of course, the question is, how can you define the right quantum immanent so that you really get everything not as the identity in the quotient, but exactly in the quantum algebra? And also, I would like to mention that this definition only works for one column or one row. Does not work in general partition. So in other words, that this definition is not appropriate for general case. So now let's see that how we can solve this problem. So first of all, let me recall the so-called non-commutative symmetric functions. Let SIM be formal non-commutative symmetric functions, which is a free associative algebra generated by lambda 1, lambda 2, and then with all this lambda k, this is an infinite sequence of indeterminates, and then the ground field is some commutative field of characteristic 0. First of all, we use this lambda k to define, we call this lambda k, we view this lambda k as elementary symmetric function. Just imagine that they are some sort of a non-commutative elementary symmetric function. So we define the infinite series lambda t to be the summation of this lambda. And then by the usual relation between the homogeneous symmetric function and the elementary function, we just formally define the sigma t to be lambda of minus t inverse. So then we call these this to be this sk to be the homogeneous symmetric function. So these are the non-symmetric. In other words, you start with the something elementary symmetric function lambda k, then you formally define this sk, and then the sk are called the homogeneous symmetric function. And then once you have that, because it's just like symmetric functions, you have a basis formed by elementary symmetric function, homogeneous symmetric function, but more importantly, you like to have the Poisson symmetric function. So then you can define the Poisson symmetric function by taking this by this differential equation. Then for that differential equation, you can write that you can write the sigma t as exponential of this thing. So this is something like a half vertex operator, and then you define this phi k, and the phi k will be our Poisson symmetric function. So remember that all these are so-called non-commutative things. We formally define this lambda k. Then from lambda k, the elementary symmetric function, we define the homogeneous symmetric function. From the homogeneous symmetric function, you define the Poisson symmetric function. So this approach is a so-called you can define the so-called Riemann-Schur function and form the base. Well, this approach is given this by this paper Gelfand, Krob, Laskow, Leckler, and Rittag and Thibon in that very important paper is 1994. So once you have that, so then let's come to the Hecke algebra. So the Hecke algebra really, I'm talking about the Iwahori Hecke algebra. So this Hecke algebra is generated by T1, T2, and so on, and Tm minus 1. They subject to the Hecke relation. The first relation, the quadratic relation, is Hecke relation, then satisfy the braid relation. And then the Hecke algebra, actually, there's a very nice representation of a Hecke algebra obtained by using the very same R matrix we defined for the quantum general linear group. So you consider the R chat. R chat is the permutation matrix times R, and then it's well known that the R chat actually the Yang-Box equation actually corresponding to the braid relation for R chat. So that's if and only. So in other words, that moreover than that, we can have if you assign Tk to be R chat k plus 1, and then we have a representation of Hecke algebra on this m-fold tensor product. And this is the representation for the Hecke algebra. And then so now let's see how do you define the quantum immanent. So we define quantum immanent in the following way. First of all, let's take the dual base of Cn, call that the Ci star. And then the regular base of Cn, we call that Ei. So then we can have a base of a Cn, the n-fold tensor times m-fold tensor, the dual base of that, and the Cn tensor n, and it can be this the product of this tensor these elements. So they will form the basis for these the n-fold this n tensor m-fold tensor. So then for any element in the matrix in this tensor product in the quantum semigroup times the anamorphism algebra of this Cn tensor m. So we can write that as a tensor in this A. This is like a multi-tensor in this way, and then the elements, the coefficient can be written as a matrix coefficient by using this the tensor basis. So we write this A. So now first of all, let's take any representation of a Hecke algebra. We can define the so-called the character of the Hecke algebra. Really, this is there is a procedure you can define the character of Hecke algebra for that. Essentially, this is some generalization of the character of the Hecke algebra for the symmetric group. You can just take the generating function of all the character values, and then you can view that as an element in the symmetric group. Similarly, you can define some character in the Hecke algebra. So in other words, character of Hecke algebra is really some special element in this Hecke algebra. So for that Hecke algebra, and as we have an action of the Hecke algebra on that. So for any corresponding to any irreducible representation, you can define this immanent, quantum immanent in the following way. So for any x, so you define to be this matrix coefficient, this special matrix coefficient, and you can check that when q goes to 1, this descends to Littlewood original definition. So, and then for any multiset of that n, and then we define this that's a usual multiplicity, and then there's a quantum multiplicity. And then by the character, I mean that the character I define the character in this way. So here this I think I missed some steps. So maybe so for any Yang diagram, you can fill in the numbers, and then you get this, and this is the standard tableau. For the standard tableau, we know that you can use the standard tableau. The standard tableau parameterizes the irreducible representation of the Hecke algebra of the same shape, and then you can define this V. Say I will just call this V lambda V t, and then this VT, they realize the irreducible representation for Hecke algebra by the usual. They can view this Yang orthonormal base, and then there is some action. You can define this, and then there is a inner product, the canonical inner product. And then using the canonical inner product, you can define this. You can define the psi element, and then using that, you can come up with the idempotent. So here I really mean that this the phi this epsilon lambda I is really the summation of this element. So, and then here we define the character by this that element, by the conjugation by all these t sigma. T sigma really means that for the for the Hecke algebra, you can define for any reduced expression of sigma, you correspondingly define T sigma, and then it's well known that the T sigma is independent from the reduced expression. So T sigma is form a linear base of a Hecke algebra. So then I'm really taking the something like a averaging of this guy, and that's the character. We call that the character in that definition. In this definition, note that this has the advantage because all these indices I1, IM, they can be repeated. In other words, they are not just the usual submatrix of the matrix. They can be this generalized submatrix. So all the indices can be repeated. In the previous definition, whatever definition, there is always this problem that if you cannot repeat the indices. But in our definition, this is really, it works in general. So, and of course, it turned out this to be the correct definition. So you define the quantum immanent. And then, as we mentioned, that also I want to remark that although in this definition, this chi, and in the original definition, the formula looks like it depending on the tableau, but you can prove that this is independent from the tableau. So the definition of quantum immanent is independent from the choice of a standard Yang tableau. So then, first of all, we have this proposition. So take any multi-set, and then the quantum immanent can be expressed by this quantum immanence of the chi lambda can be rewritten using the idempotent, Yang idempotent, and then with the multiply by the summation over this sigma, and then it will have that the multiplicity. So now let's look at the Schur-Weyl duality. So in other words, we have that Kostant's result of interpretation of the usual immanent for the zero wave space. Now we are going to talk about it in the general wave space. So here we consider the Schur-Weyl Jingbo duality. Here U lambda is the irreducible representation of the quantum algebra GLN, and V lambda is the representation of the Hecke algebra. And then there is a natural co-module, because here we work in the dual algebra. So there is this is co-representation. The co-representation is defined from the Cn tensor m-fold tensor to the Cm m-fold tensor times the quantum semigroup. The action is given by the tensor to the summation of this tensor with the matrix with all these elements coming from the quantum semigroup. And then you can prove that this is really satisfy all the necessary conditions for the co-module structure. So it is really, this is a dual representation of the UQSAN acting on this Cn fold tensor because there is a usual Cn is fundamental representation of Gin. So the Cn, the m-fold tensor, because quantum algebra is a co-algebra, is a Hubble algebra. So then there is a representation of quantum Gin on that tensor. And this is just a dual representation because we're looking at the dual group. So then let's take the for the representation of the quantum algebra. There's the base is so-called. We have this Gelfand-Tsetlin base that we call that the Kc lambda. And then for the Hecke algebra, we have the so-called Young base. We call that the V tau, Vt. And then we can take the tensor of these two, and this is going to be a base for that for our representation space. All these space, of course, we normalize them to be orthogonal. So we define there is the standard inner product so that they are orthogonal to each other. Then let's look at the weight space, mu weight space of that space, and then there is a projection from the V lambda. The projection P mu is project to the mu weight space, and then since we have a co-module structure, and then under the co-module structure, this was sent to V lambda tensor the quantum semigroup, and then we apply the P mu projection again. And then so we project to this mu. And then recent work that we prove that for any lambda and the multi set of n, mu is any composition such that the mu I, the multiplicity of mu I equal to the multiplicity of this index I. Then the quantum immanent, normalized quantum immanent is equal to the trace identity of this. And you have the projection operator tensor this co-module structure map, and then this P mu, and then restrict down to P lambda. You take the trace, and this trace turned out to be exactly the quantum immanent. So in particular, when you look at the so in the special case, when m equals n, when mu equals the one row, the one column, then we establish a quantum analog of Kostant theory provided on the zero weight space. But note that our result is for any weight. In other words, we have the quantum interpretation for all the weight spaces. Answering that question. So I think how much time? Okay. So now let's look at the quantum Littlewood correspondence 1. So corresponding any relation between Schur function, we can replace the Schur function by the quantum immanent of the corresponding principal minor, provided that every product is summed by all sets of these complementary principal minors. In other words, in the original Littlewood correspondence, all you do is just put the quantum over there, and using our quantum immanent definition, everything is true. So that's for the Littlewood quantum. So in other words, that if we have a Schur function, the product of a Schur function, and then you get a corresponding quantum immanent identity, and this the summation is of all disjoint subsets of these. And then so now as a correspondence, we get a Q analog of Littlewood-Merris-Watkins identity. So of course, this identity was quantum immanent was proved by Kavanica Skandera in 2011. Uh, by the way, so if we specialize the trivial case, then our definition is the same as the Kavanica Skandera in the special case, in one row case, in one column case. And then for the so now we got this immanent for the trivial, the induced trivial character, induced sign character. You got this quantum determinant, and then here for the induced trivial character, you got immanent to be expressed as product of the quantum permanent. And this is a sum over all the usual case. Well, the determinant and the permanent are defined exactly similarly like before. You have a usual determinant, quantum determinant definition. And then Littlewood correspondence Q. So if you take any xi to be generalized principal submatrix and whose row and column indexed by this one. So in the generalized principle, meaning that all the rows and columns can be repeated, and corresponding to any relation between Schur functions, you may replace each Schur function by the corresponding normalized quantum immanent of the complementary principal minus, and then take all the corresponding sums. So in particular, for example, if we have the Littlewood-Richardson rule over there, then you correspondingly get all this identity for the quantum immanent. And then in particular, we get a Q analog of the Littlewood-Merris-Watkins identity. So you take a multiset of M, fix a partition of M lambda, then the quantum immanent for the corresponding to the induced quantum induced sign character for the Hecke algebra, and this can be expressed as a product of the determinant of the submatrix I1. And then correspondingly, if you consider the trivial induce the trivial character of this for the Hecke algebra, and then you get the immanent can be expressed as permanent, but then you have to modify by these normalized constants of the multiplicity. So this is the Littlewood-Merris-Watkins identity. When Q equals 1, this descends to the Littlewood-Merris-Watkins identity. Now, let's look at the quantum Macmillan master theorem. So now define alpha 0, alpha 0, beta 0, and 1. And then you can define alpha k to be, this is the sign, that's the idempotent corresponding to one column. And here, this idempotent corresponding row, you can define alpha k and beta k. And then this, in the quantum, then you can define corresponding the generating function lambda t. Lambda t is really the quantum analog of for that elementary symmetric function. So these are something called the alpha k will be something like quantum elementary symmetric function. This beta k will be something like quantum homogeneous symmetric function. So then you can define here, and then in the quantum A matrix over here, we have this identity. And then we can, if we consider the Q permutation, PQ as being that Q permutation, and then using the Q permutation, we can define the product of the Q matrices, Y and Z, the star product, which is the partial trace of the Q matrix times this Y1 and Z2. We define that to be this. And using that to be the iterated power of this X, so we can find this X0 to be 1, X1 power to be X, Xk to be the K minus 1 power, and the star product with X. And with that, then you can define the quantum the sign, the quantum case, the summation. with this, and then we have we got the following Newton's identity. This following Newton's identity really follows from the quantum Macmillan master theorem. So in the quantum semigroup, we have this. If you take the derivative, you have this, and for the lambda and the sigma. And then we also have a Q Goulden-Jackson identity. So you consider the Jacobi-Chudy matrix for A, for that of a transpose lambda, and then for beta, you get a beta lambda. Then you take the determinant of this Q, and that determinant can be expressed as a quantum immanent, or with all this. And then we can also consider the so suppose that we can consider this in the quantum semigroup. We consider this characteristic function for this alpha k, for this x. We call this alpha. The Q characteristic function is defined similarly. I mean, in this way. So once you define this, then we can have that. Suppose this omega 1 omega n to be the solution of this the Q characteristic polynomial. Then the quantum immanent, the Schur function can be expressed by the quantum immanent. In particular, in the special case that you have elements with symmetric function expressed as the quantum determinant, and then the homogeneous symmetric function expressed by quantum permanent, and the power sum to be the trace of the x power. So, and finally, we also have that the alpha k actually turned out to be they generate a commutative subalgebra, and so this is the beta subalgebra generated by alpha k. They actually isomorphic to the algebra symmetric polynomial with n variables. So all these alpha 1, alpha this, they commute, they generate the. So that, I think that's the end. Okay.
Thank you. Any questions, comments? Please.
Can you remind us what is the product?
I'm sorry, which
so
product?
Alphas are commuting with respect to what product?
The usual product. Because they are defining the elements in the quantum algebra.
Right.
Because in the quantum algebra you have all these variables, they don't commute in general.
Okay.
So this alpha k are some elements in the quantum coordinate algebra.
Okay.
So in that algebra, yeah.
It takes some time. So thank you for the nice talk. And my question is, so this is related to the standard RTT or whatever.
Mm-hmm. Yeah.
Is there any analog of this construction for the reflection equation?
Not yet, but yeah, we are considering that, but not yet. Not unknown. I mean.
Okay. More questions, comments?
Yes.
Immanent for the quasi-determinant case.
Which determinant?
Quasi-determinant.
Quasi-determinant? I don't know.
No.
I was just wondering if you take not quantum matrices corresponding to quantum GLN, but orthogonal or symplectic, do you still have anything like this?
Yeah, that's the same. Yeah, for that we are working on that. Yeah.
Okay. Okay. All right. So if there are no questions, then thank you again.
Thank you.